In this question, we'll be solving a question related to Gauss's law. And the question says, a spherical shell of radius R has a total electric charge Q on its surface. Then the first question is, what is the electric field inside the shell? So for us to solve this question, we need to keep in mind of Gauss's law. And we have that the electric flux phi E is equal to the closed integral of E dA is equal to the Q enclosed divided by the permittivity of free space. And if we consider this to be a Gaussian surface, and this is a spherical shell, right? Take for instance, if I have a metallic conductor, for instance, I have a metallic conductor as well. Let's say this is what I have. Then we normally have the excess charges at the surface, and this is the metallic conductor. So this is the Gaussian surface. The Gaussian surface, and we have this, and we still remember that from our previous video that we explained what happens here, and the electric field inside will be zero. The same thing as the total charge enclosed will be zero as well. The reason is because there are uniform charge in here, and for the fact, so there are uniform electric field in here, and for the fact that the electric field is uniform, then it is zero. So, and that's why the same thing is applicable here, and electric field inside here will be zero because the enclosed charge as well is zero. So we have E to be zero. You can check up the previous video for a better understanding of this. Then the second question says, what is the electric field outside the shell? Yeah, the electric field outside the shell will not be zero because you have charges displayed, the excess charges surrounding this area. There will be excess charges outside. So in this case, it will not be zero. So we'll have the electric field and the flux using the same formula, the flux to be this. So we have that EA is equal to Q naught, Q. Now the charge enclosed here is Q. Okay, let me just say it enclosed divided by epsilon naught. And the shape of this is a sphere. So the area of a sphere is 4 pi. Area of a sphere is 4 pi r squared. So this is what I have, and the charge outside this will be Q divided by permittivity of free space. So with this, we can make the electric field a subject formula, and we have that the electric field will be Q, okay, 1 over 4 pi epsilon naught Q divided by R squared. So this is the electric field outside this. Then the next question said we should calculate the potential outside the sphere. Then how can we calculate the potential? We will do that using this formula. Okay, let's go down and have a space to write. The potential outside the sphere will have the potential to be, okay, this is 2.3 or 2.3. So the potential V is equal to the integral, negative integral of EDR from infinity to R, because since it's outside the sphere, we consider a situation where we move from the infinity back to the normal radius. So we've gotten the electric field to be this expression. Right. So now we have to like integrate this with respect of R. So I can say that my V will be equal to the minus integral of minus infinity. This should be minus infinity to R Q divided by 4 pi epsilon naught R squared, and we can factor out some constants, which is minus Q divided by 4 pi epsilon naught. Then we are integrating R 1 over R squared dr. Okay, there should be dr here. So to solve this, let's first of all integrate this. So integrating this 1 over R squared minus infinity to R dr, this same thing as minus infinity to R power minus 2 and dr. So if you integrate this, we'll be having R to power minus 1. That is minus, because divided by minus 1 as well. So minus R power minus 1, then from minus infinity to R. So, and this will be equal to negative 1 over R. So if you plug in the limit of integration, you will be having this. So if we decide to substitute this back to this, substitute back to this expression now, since we've gotten the integral to be negative 1 over R, then we can say that the V will be equal to minus Q all over epsilon pi 4 pi epsilon naught multiplied by minus 1 over R. Then we have that the potential will be equal to Q. Okay, let me rewrite it in this way. The potential will be equal to 1 over 4 pi epsilon naught Q over R. I believe this is very familiar to what we know as the formula of potential. So the next question is, we should calculate the electric potential inside the sphere. We should calculate the electric potential inside the sphere. Okay, let me change the color of my pen. And for us to calculate the electric potential inside the sphere, we have to like think, because from basically looking at the first question, we find that the electric field is 0. And if you apply this formula here, the formula over here, you will think that the potential inside will be 0. No, it does not apply that way. Since the electric field inside the sphere is 0, okay, let's assume this is the sphere. The electric field, since the electric field here is 0, you have to notice that there is a uniform potential inside here. So the potential is uniform. Okay, so it doesn't change. So and the potential is constant. The potential is constant. It doesn't change. So this experiment, you can do it in experiment as well. Maybe you have a tray, a plastic tray, you pour in your water, and you have a spherical shell and put it there. then plug it to the AC volt and try to measure the potential inside. You realize that the potential inside this is constant. So in that case, we have the potential, the electric potential to be equal to 1 over 4 pi epsilon naught Q over R, which is the same thing as the potential outside the sphere. Thank you for watching this video. If you have any question, feel free to reach out to us at science nasalifa academy@gmail.com or science e-learning academy@gmail.com.